Hello and welcome to today's Code Presents. I'm Philipp's virtual avatar and I will introduce today's session. Today we will discuss the possibilities, limitations, and impact of generative image AI. We'll talk about how models like Midjourney, Stable Diffusion, and Flux work, how they can be used in combination with other technologies like large language models, and how they can be adapted to specific use cases. Before we get started, I will hand this off to the actual me, so he can briefly introduce himself and the code group.
Thank you for that introduction, me. Well, that was a good demonstration of the capabilities of image generation. But before we dive in, let me share a little bit about myself. I am a senior software architect at Code Consulting. Over the past 15 years, I've worked in various domains ranging from front-end and back-end development to server administration, deployments, and DevOps. Currently, I collaborate with our clients to integrate machine learning models into their applications. If you have any questions after today's presentation, feel free to reach out to me at the email address provided here. Now let's take a moment to discuss the code group. Code has been dedicated to help individuals and organizations build better software for an impressive 30 years. Our approach utilizes the expertise across our 4 divisions: consulting, staffing, training, and our magazine. In the consulting division, we offer custom software development, co-pilot development, AI solutions, GPT implementations, and leverage our extensive Azure offerings. We also specialize in project rescues and modernization efforts, alongside providing ongoing support and maintenance for existing applications. If AI consulting services pique your interest, I recommend exploring our new executive briefing offer. In these briefings, we demonstrate how your organization can effectively leverage modern AI technologies in its applications. For more information, please visit the links displayed on your screen. I also want to highlight our exceptional staffing offerings at Code Staffing. Our staffing division is revolutionizing the industry by prioritizing the well-being of our employees. We ensure that our staff enjoys full benefits as employees, not contractors, which has led to rapid growth and employee satisfaction within our staffing division. If your organization has staffing needs, please visit codestaffing.com to connect with us. And for those interested in joining our team, we're always on the lookout for talented individuals to apply. Here's what we'll cover in our session today. First, we will talk about the capabilities and limitations of image generators. We will then talk about how latent diffusion models work under the hood. So what happens when you click generate after entering a text into your prompt field. We will have a look at the impact of generative AI on the industry and society, and then we'll finish with some concluding thoughts. So, first of all, let's talk about the capabilities and limitations of image generation models. Here, I have a couple of images that I generated for this presentation. If you look close enough, you can see that they are hardly distinguishable between real photographs. And in this example, one of these 2 images is an actual photograph and the other one is a generated one. Could you tell the difference? There are a couple more examples here of images that were generated with the latest generation of image generation models. All of these images work for one of our clients who's actively using this kind of model in their work. But not all outputs are good. Oftentimes you find images generated with illogical elements in it, like a hand with 6 fingers or huge pills. This is because image models and video models and language models, for that matter, don't really have an understanding of the actual world. They are creating facsimilies of it, and they don't necessarily always make sense. Because, for example, you can see in the middle image here that the placement of all of the items on the surface are very much random. And you see these kinds of faults oftentimes with cutlery, or if you look at images of food with asparagus being sorted in or strewn all across the place instead of being neatly placed on the plate. A really interesting and important ability of image generation models are their ability to be trained. And I have this demonstrated here with some examples of our code magazine. What I did here was I used a vision language model, a multimodal model, to describe our magazine covers. And these images were then used to train a low rank adapter. And I generated an image just based on the text prompt of just with the base model. And then I used my adapter to generate the same image with the same prompt. And you can see the results here. The first image of each group is just the base model itself. Then we have the training image. And after training and applying that low rank adapter during generation, I got a image that is far closer to the actual cover that was generated. So these kinds of things are very valuable for doing things that require a certain style, for example. You can see here that the code logo itself has been pretty accurately trained into the model already. And this only took a couple of images and was a fairly quick training job. What you also notice on these images, though, while these newer models are handling text fairly well, they do make mistakes. And another important drawback of these models is that you have no real control over where individual text elements, for example here, are positioned on the cover. So image generation models are not necessarily the first choice when you want to have a consistent layout or something that you can control to a high degree. What you can do, though, is generate the background artwork for a cover like this. And we have actually used image generation models for some of our recent covers. The ability to create text, again, has been realized with very recent models. And for short words, this starts to work really well. You can even give it a description of how the word should look like. So in the first example here, I created an image of a sushi bar and asked the model to write the word yummy in crab legs hanging above a piece of sushi. So I think it handled that pretty well. I mean, they are not quite crab legs, but it's kind of like that crab cake that you can get. The next image shows a man holding a beer into the camera, and I asked the model to generate the word cheers above it in foam. So, and it accurately, I think, generated a text that looks like foam. The other two images show just some more versatility with these models and that they can handle different kinds of situations. But these are cherry-picked examples, and until I got some good ones, I had a bunch of rather hilarious failures. Another interesting feature of image generation models, and this is not necessarily just limited to diffusion models, but we're talking generally here, are features that can, for example, colorize images. These models have been trained on a bunch of images that one was black and white and the other was the colored one, and then go from a black and white image to a colored image. And it does a pretty good job. Let's take another look at this from the black and white to the colored image. And I can attest to that this building just above my head here does indeed look pretty much like that. Another interesting feature is the ability to upscale images. And I'm not just talking about resizing, but really upscaling and adding more detail into a picture. It's not finding any detail. It's not like one of those old TV shows where they say enhance and they find actual detail in video camera footage, but rather it invents more details. It generates them just as it would generate an image from scratch. And the current image that we're looking at has a resolution of 1024 by 576. And this is the output resolution of the model itself. And then what I did was I applied a upscaling model that then generated a new image with twice the resolution, in this case 2048 by 1152. And you can already see that there are more details now in the feathers and around the face of this bird. And then I went another step higher, doubled the resolution again, and you can see that there are even more details in this picture now. If we take a look at all of them side by side, this effect becomes very apparent. A very recent development with image generation models is the extension of going from images to actual videos. And these video generation models now can generate videos up to about 60 seconds. This particular one was prompted with the following caption. We orbit around lighthouse, hyperdynamic movement and orbiting motion, shallow depth of field, subject in focus, and a dark and gloomy style. If we look at this, it definitely gets the style right, I think. And it does a smooth pan, and you will oftentimes see this with these videos, that there's like a slight panning effect or a zoom effect. And the more recent models, they get quite dynamic in some instances. And there's a lot more to come, I think, here. What this also enables is to filter out, for example, from a video, a person's pose, how they walk, and all of that, using models that replicate the bone structure as lines in an image, making a kind of a stick figure out of someone. And then image generation models or video generation models can use this data to superimpose a generated a person or something like that that moves in the same way. So there are also cross-generation features, so to say, where you can use multiple models to work together to create a new image or a photo or video based on existing data. This is what's called an image-to-image model pair. Then an important thing to be aware of is what's called prompt adherence. So when we add a prompt into our model, if we prompt it with any kind of text that any description that we want to have, it is still problematic for models to correctly transfer the content from a text prompt into an image. And you see this become better and better over time, but here, for example, with an older model trained on our CodeMag images, fails to properly generate the little details that are mentioned here in the yellow highlighted text. So instead of doing these icons and gears in the cloud, it just generates a train without actually following the prompt. It does a good job at doing the style, right? The green highlighted text, but the rest is just not quite there. Compare this to a newer version that I built of this low-rank adapter that I just showed you earlier. This new model does a way better job at adhering to the prompt itself. Here we see all of these little details that are described in the prompt itself. A really good technique that you should know about when you get into this, if you want to automate some things and help your user along, is enhancing prompts, image generation prompts, using large language models. So instead of just putting teddy bear into your model and getting a teddy bear, you can ask the large language model to improve that prompt and then generate based on that output. And now we still see here also some prompt adherence issues, that the bear is not holding the basket itself. But these are not necessarily things that a language model alone can solve, but it can help us giving more detailed instructions to an image generation model to follow our idea more closely. So some tools that you can use for this are just simply online platforms. There are several available where you can just put your prompt into an input box and hit generate, and you get an image. You can even do this in products like ChatGPT, just within the chat itself these days, or in Microsoft's Copilot as well. It can generate images on the fly. Now, the problem with that is control. And we as developers, of course, need some more control for these kinds of operations, and we want to automate things. We can't just build our application based on a chat prompt from OpenAI, for example. So we need something that we can fine tune, configure to our needs, and also use with an API. And there are image models that you can use on platforms like Azure OpenAI that will work perfectly fine, usually for more basic scenarios. And then there are the kinds of configurators like Comfy UI here that you see, node-based workflow configurators, where you can precisely steer each and every single parameter of the model and its execution. So this is very valuable when you have to implement a more complex workflow. Let's say generate an image, outpaint it, which is the ability to fill in new content around an image that kind of integrates with the content. So let's say we have a square image and we want a white aspect ratio out of it, and we don't want to just crop it, right? We don't want to lose information. So we can use this kind of technique of outpainting to add more content that fits with the already existing content. And then we might want to go and upscale these images as well and do that in one workflow. So we could, use these tools to visually configure these workflows, which makes it easy to work with, and then later use these workflows and build an API out of them. So there are very interesting ways of using this and then shipping this out for use in your application. How do latent diffusion models work? So, latent diffusion models are the previous generation, let's say, of image generation models. Stable diffusion comes to mind here. Newer models also use transformer-based model approaches. They have evolved over time. But due to the complexity, I want to give first an idea of how all of this works without getting too deep into the weeds. So, in short, it's magic. So, with that covered, thank you for attending today's Philipp Presents, and I hope you learned a lot in this presentation. Of course, it's not magic. No, it's a combination of many techniques that have been developed over years to get to the point where we are today. And one of the most important pieces of it is segmentation. So basically, how can we even find objects in images? Just the real basic idea of recognizing something on an image. Where is it? How is it positioned? What is it? So we need this kind of segmentation just to even get to know where in the image anything is. So there are multiple different kinds of segmentation. There are, as you can see here, just very simple segmentation of one thing in the image here, the very basic. And then also you see instant segmentation on the left hand here, with how you see the street scene is then segmented into different kinds of objects, from pedestrians to cars and so on. And the way that this is done, and a lot of things in computer vision are done, is with using neural networks. And at its simplest, or its base form, a neural network has many layers that are connected with each other, fully connected layers. And with these kinds of models, in the early phases of computer vision, we were able to use a fully connected layer network with the MNIST data set, which is basically a collection of handwritten numbers from 0 to 9. And they're all represented in this neat little grid of 26 by 26 pixels, black and white, or grayscale, let's say, one channel. And with all of these images, we have an input size of 784 pixels, so 28 by 28. 26 by 26, sorry. And we have 10 different possible output values, again from 0 to 9. So with this, we look at about 7,840 connections to train this model and then output its predictions. That's still manageable. 784 is still pretty good, manageable. But if we now think about images that we encounter from in our everyday life, or if we have already used one of these models, they're usually about 1024 by 1024 these days. If you just think of 226 by 26 being 784 inputs, well, let's think 100 by 100. That's already 10,000 inputs. And then we don't just look at generating outputs for numbers or 10 outputs. We want to generate a new image later. So another 100 by 100 would be, again, 10,000 outputs. Now we look at 10,000 inputs and 10,000 outputs for 10 million connections instead of the 7,840 that we've represented with this one. And this just grows exponentially. A 512 by 512 image would have 262,000 inputs and outputs. And this is only in one channel. Now multiply all of this by 3 because we have colors. So it becomes a really big problem really quickly on the computational side. What is being done about that is pretty ingenious. Instead of taking everything in at one go and with the image, we analyze the image and extract features by using convolutional kernels. And these convolutional kernels are basically grids of varying sizes, 3, 5, 9, kernel sizes. And these are being shifted across the image, like a grid. And row by row, it goes through it and kind of summarizes the values that it finds within its little window that it has. And all of that, then kind of, if you do that enough times, you get features extracted out of the image that can be analyzed a lot easier. Some of these filters or kernel features will look something like this, where you detect edges, where you find different orientations of features, and all of that eventually leads to getting a mask out of this. Now, it just doesn't work with convolutional. That's not how you get this mask that you see behind me. There's more involved with that, but convolutional layers are definitely a big part of that. So what is that? That is the UNet architecture. This is a neural network architecture that leverages not only convolutional layers to extract features, but it downsamples the image over multiple steps to get connections between pixels that are further apart by, instead of widening the kernel, which leads to increased computation, we stay with the small kernels that don't need a lot of computation, and we just decrease the size of the object that we're looking at. So our lens kind of shifts, we get more connections throughout the image, and that helps us make sense of what we see in an image. So there's our downsampling step. These steps here on the left-hand side is our downsampling process. And in that downsampling process, we extract our features. And after we've done that, we're using the other side of the UNet. And this is where the name comes from. It goes down and up again. And with all of the information that we collected in the downsampling step and with our convolutional layers, we can then construct the mask that we are looking for. And we're doing that by way of upsampling and adding the information from the downsampling tasks as well. You see these gray arrows here. These are skip connections that work their way from one side to the other. And with that, over time, during our training, we get a network that can handle these kinds of segmentations. And these are, by the way, the images that you see here are the image for usage in training, and then the ground truth. So just as a refresher, whenever you train a model that is trained with a truth, and it's so a supervised learning model, you always have something to compare it to. So your ground truth, or for us, it's these masks that you see in this group of photos. Diffusion models are then a next evolution, so to say, of the UNet architecture. What people have been thinking about with these image segmentation models was, can we use this to denoise images using a model like this? And what they found was that, in principle, a image that has noise is pretty much like an image that has no noise, and we add some noise to it. So if we can add noise to it, then maybe in the same way that we can find shapes in an image, maybe we can also detect the noise and remove the noise. Because a clear image at the end of the day is just a noisy image that you remove the noise from. And this has been pretty successful. So we just train our model by giving it an input that is noisy, and we give it the exact noise. And over time, we can train it to remove noise from an image over time. And we do this in multiple steps that we explain to the model. Hey, you have these many steps to denoise. And this is kind of our positional encoding within our model. At each step, we instruct it to do more and more of this denoising. Going from just the noise to the original image is too hard for it to do, of course. The most efficient ways is to do this one step at a time in slow increments. And this yields a denoise prediction at the end that goes from just noise to a little noise to no noise. And by doing that, this model already knows how to get from a noisy image to a non-noisy image. If you just give it noise now, what will happen? It will generate an image. It will remove the noise from just random noise. And eventually, you'll have an image. Now, at this point, the model doesn't know what exactly to create. It just denoises something, right? This could be absolutely anything, not even an actual image of something. It just doesn't know really. But up until now, we've thought of all of this in terms of pixels. But denoising images with actual pixels is still a hugely computational task. What we've seen was exaggerated in its size just to make a point, but early models that used diffusion were limited to just a few pixels, basically. What we can do to get around this kind of constraint is to use a variational autoencoder to encode the image pixels into the latent space, which is basically an embedding. And these variational autoencoders encode the incoming data and transform them in this latent space where they are not quite the actual image anymore. They're more, let's say, the idea of it is saved in this latent space. And then later on, we can extract that again by way of decoding the data from it. And this latent space can be represented in multiple dimensions. It is a space made of n dimensions, so basically a 1,000 dimensions plus. So to just capture all of the intrinsic information in the output of our model, of the encoder model. And for our MNIST model that we were looking at earlier here, this can be displayed in this blotchy colored image that you see here. And when we go over each of these colors, we see that each of them represent a number. But we can also see that while we go over this, it's all kinds of different shapes of each of these numbers. So all the sixes look like sixes, but each six looks a little bit different. And in the same way, when we think of more complex concepts within an image, these kinds of concepts are embedded into the latent space. And it's kind of like, I explain you a new kitchen layout, and we both have a somewhat different kind of idea of what that actually looks like. And in the same way, the latent space is not an exact representation of a singular thing. It's just the idea of it. So we can now take our image and turn it into latent space, add our noise, and train our model based on the image in the latent space. And that's where the addition of the latent comes to the latent diffusion model moniker. So during our generation process, then we use a latent image of noise and then remove the noise, and then we decode it and get our image. Now, again, this is still not actually knowing what it would generate. It is just generating. So now we need to somehow make this whole network controllable. And for that, we'll take a look at text-to-image generation, finally. So up until now, we had no control, and now we need to think about how can we even start to tell a model that only knows a lot of images with noise and without noise, how can we tell it what these images are about? How can it learn that certain words are related to certain features within our images? And we can do that by embedding the text itself also. We encode the text with a new model that we'll introduce in a second. And then we can align both features. We can align the features of the text, and we can align the features of the images. So similar to how the features are extracted from images, they can be extracted from text. And instead of convolutions, now we're looking at things like self-attention layers from the transformer models. This is all beyond the scope of this presentation, but we'll take a look at this just in a short, shallow form. So we have our image, and we use a convolutional encoder to portray that as a vector of floating points. And now, if we take a look at our text, we can use a self-attention encoder to also turn this into an array of floats. Both are these embeddings in our n-dimensional space. Now, what we need to do here is we need to make sure that both of these embeddings are basically saying the same thing. So we need to train our models together so that both are representing the same kind of vector in latent space. And this was done by OpenAI. They trained a model called CLIP, or Contrastive Language Image Pre-training, and they used about 400 million images to train this. And now we have a model that comes out with similar embeddings for both images and text representations. And with it, we can embed all of these things into our unit structure again at the pivotal points here where we do our generation, our feature extraction, and so on. And then we have successfully trained a model that can denoise an image from very crude. Let's play that again. These are actual steps in the generation itself. And it knows which part of a text is which part in an image. So now, after we learn what they're useful for, what their strengths and weaknesses are, and that we learn how they work, what is the impact of generative image AI on industry and society? And what does it mean? What kinds of pitfalls are there even for you if you want to implement it? And one of the pretty big things that has been in the media for a while now is the collection of training material, which has been viewed as critical by some, especially many artists that are protesting against how these image models were trained by using their images without their consent. So there are some ethical considerations, and some of the bigger companies that have been working on their models, they have shifted to use their own licensed data. For example, Adobe trained their image generation models using their own licensed data that they have on their platforms. Another issue is bias in training data. So as with many other computer vision models, they very much are a child of their data, of what you put in. What you put in, you get out. And curating data sets in a way that these biases are minimized is crucial. And we should opt to try to get these kinds of models more and more diverse in that sense. You can still observe that when you just put in a simple prompt of an engineer who's working at a server data center, you will usually get a white male guy with a blue shirt and jeans. And in your practical day-to-day use, this can lead to some unexpected outcomes in the image generation, where it just becomes dull. You might need something more creative. And again, this is where those enhanced prompts would help a little bit. If you instruct your large language model to keep an eye on how to phrase the prompting for the image generation model. Then you also have the responsibility during your product integration to make sure that you implement it in a way where no harmful content can be generated. On the copyright front, you have to keep in mind that any image currently that is generated from a model is actually not copyrightable. So none of the work that you generate with a model can be copyrighted, and everyone who gets a copy of it may use it as they please. Now, on the other hand, you can also generate copyrighted IP. So, for example, some models are capable of generating an image of Mickey Mouse, and you're obviously not allowed to use this kind of work or output to then sell as prints on t-shirts. So definitely something that you have to pay attention to. And with open source models, if you are using those, each model has their own licensing agreement, which needs to be adhered to. There's also still in late 2024 an absence of settled case law and legislation around image generation models. Currently, some cases are still making their way through the courts that may impact how or if you can even use a model for your use case. So things to keep an eye on. In the live presentation that I gave a while ago, I showed this about slide of me with this image here. And in it, you can see this is based on a model that I trained. And this model was generating a couple of pretty good impressions of me. And at a distance, you wouldn't even really notice that this was not a photograph, especially on a projector screen. So I used it to make a point. This point was that, hey, this image that you saw earlier of me wasn't actually real. So you need to be careful to trust what you're looking at in today's media sphere. As you can see, not all of these deepfakes were really successful. They do look a little off. You have the comparison in front of you. You can see it. But you can also do some really fun stuff. So if you want to have this kind of ability to just do some creative stuff, it definitely is a great tool for that. And you can have a lot of fun with it. Same thing for artists these days. They may use these kinds of models in their day-to-day toolset. And the same thing when it comes to deepfakes to videos as well. So this is just a short clip that I generated. There are, again, earlier I was talking about how you can extract movement from a scene, a video with one model and then superimpose another generated person, for example, on top of it. That can definitely lead to serious consequences when it comes to misinformation. And you've seen the intro, the model that was generating the introduction to this code presents. It gets pretty good already. The model was trained from a short video, just about 2 minutes, and was able to fairly decently replicate my likeness and my tone of voice. It is a little bit uncanny, granted, but these are early kinds of models. And all of that, of course, on the societal impact side of things, we have to be aware of these kinds of images. We need to be aware that they can be used against us, and that we need to be vigilant with our media that we consume. There are certain measures that researchers are trying to put watermarks on generated content, and to some extent, in my opinion, it may work. To another extent, it seems like if you embed metadata invisibly or invisible onto an image is what they're doing. Kind of a computer can see the metadata, that watermark, but the human eye can't. But things like compression artifacts, modification of the image will easily destroy these watermarks and render them useless. For companies, the use of image generation models has already led to the loss of reputation, as you can see in these examples. If you have a very well-known brand and you have made commitments even to not use AI in your art, like some did, and then still do it, your community will have some complaints about that. It is very dependent on your target demographic of how and where you are able to use these kinds of image generation models. So, in conclusion, we talked today about the capabilities and limitations of what they're good at, what they're not good at yet. We have discovered how diffusion models work and talked a little bit about the journey of development to get to latent diffusion networks. And we had a brief overview of the impact of generative image AI surrounding what the pitfalls are, what you have to pay attention to, the kinds of deepfakes and disinformation that are out there, and what it might mean for your public relations when you use these images. So, thank you for viewing this video of Today's Code Presents. If you're not already subscribed to our channel, while you're here, please subscribe and ring that bell to always get a notification of our new videos. And also check our codemac.com events page for upcoming events. If you're not already a subscriber, feel free to use the subscription link here or scan the QR code to get a free script subscription for our magazine. And please feel free to share this link with your friends. And if you're watching this live today, you have the chance to win a $100 Amazon gift card if you fill out our survey until end of this Friday. So I will answer a couple more questions in the chat. I'll see you there. And if you want to get in touch with me at any time, feel free to send me a message either at my email address at pbauer@codemac.com. Find me on LinkedIn or on Blue Sky. So thank you very much for attending today's Code Presents, and have a great day. I'll see you soon.